Okay.
Is the notes not available on Blackboard yet?
Is the
These notes.
it should be. Yeah, from 9 o'clock, I think it was. Yeah.
Just refresh it. It'll happen recently.
Yeah, you need to refresh it. Okay. So last week we were looking at how we can use a process of filtering on images to enhance their quality. Okay. In principle, we might, in some circumstances, I suppose, want to reduce quality. We could use filtering for that as well, but generally, in medical imaging anyway, what we want to do is enhance the quality to get the most information out as possible. And last week we did all this in real space or in the spatial domain. So we were carrying out operations, filtering operations on the original image in real space. Okay. What I want to look at today is how we can do this filtering, not in real space, but in spatial frequency domain. So to do this, we need to understand a bit about images and how images are made up of contributions from different spatial frequencies. And each spatial frequency is going to contribute to that image and some information to the image. And we can enhance an image by performing operations that are going to reduce or enhance particular spatial frequencies. So we can transform an image into Fourier space, perform some operation on a particular region of that frequency space, and it could be enhancing or reducing. Okay, so for noise, for example, we would maybe want to reduce those frequencies. For the signal part of the image which we're interested in, we would want to enhance that. A very important part of this is Fourier transforms. So we have just a brief sort of bit of revision on that, although Fourier transforms are part of physics degrees. So as physicists, we should all be familiar with the use of Fourier transforms. And then we'll look at a number of different types of frequency filters. Okay, low and high pass filters. The Butterworth filter, we'll do that's what the assignment this week is about, is using Butterworth filter. But as I said, as physics or engineering graduates, you should be familiar with the concept of the Fourier transform. So that the basic idea of Fourier's theory is that any signal can be represented by, strictly speaking, an infinite series of sine waves. Okay, but we can also, we'll see, to a sum of a large number of sine waves can be just as good in some cases. Okay, and we can see this here. I've done some examples. If we just have a single sine wave, single frequency, we get a waveform that looks something like this. If we add in another frequency, a sine wave with 3 times the angular frequency there, and then divide the signal by factor 3, and then continue adding 5th order, or 5 times the angular frequency, a contribution with 7 times the angular frequency. What we end up with out here is, you can see we've got the underlying high frequency, or the fundamental frequency component, and then these additional frequencies on it, which we can see. Okay, so any repetitive waveform, we can express it as a sum of sine waves of different frequency, and also magnitude and phase is important here. Okay. So again, this is just sort of trying to illustrate that. If we have these 4 waveforms, I can't actually see from here. I think they're maybe slight. I think they're all in phase probably, but certainly different amplitudes and different frequencies. If we add these together, we get a sort of composite waveform that looks something like this. Okay, so this sort of illustrates the fact that we might measure some sort of signal. It might look like this, and we can decompose it back into its frequency components. using Fourier analysis. Okay, so that illustrates that quite nicely. The question is, how do we work out what the frequencies are that are present in a signal? Well, the way that the Fourier analysis works is that if we have a signal, a repetitive signal, we multiply the signal by some reference sine wave of a particular frequency, okay, and then we integrate that product. That the integral will be non-zero only if the signal has a component which is always in phase with the reference signal. Okay, so what we do is if we multiply with a particular frequency, then the only non-zero component will be that frequency component that matches the frequency in the reference sine wave. Okay, so you can see this. What we've done here, if we have frequency u, multiply if we have both two signals with the same frequency, we're going to get something like this. Okay. If we then have a product of two different frequencies there, okay, we're going to get a signal that looks something like this. Okay, that's what this product looks like, and the integral of this is actually going to be 0. Okay, so only when the situation arises where the product, where the frequencies match, do we get a non-zero integral. So mathematically, we can sort of put this. We're going to essentially, if we've got a reference signal here, okay, and we're going to multiply it by lots of different sine waves of different frequencies, okay, and then we're summing all those up. The only non-zero one is going to be where the frequencies actually match. Okay, so we've got a way of determining the frequencies that are present in the signal of interest. Okay, and this is just shown in one dimension, or we can extend it to images in 2 dimensions. The other issue is, what if they're, where those examples I showed you is where they're exactly in phase. Okay, let's take the sort of nice example where the two frequencies are exactly 90 degrees out of phase. What happens to this product and the summation then? Okay, well, here's the example of that. So we've got a sine wave of a particular frequency multiplied with another sine wave, the same frequency, but shifted by 90 degrees, or pi by 2. Okay, so if we work out this product, the integral is going to be 0. Okay, so if we can multiply by a cosine in this situation. So we need to include cosine and sine components to deal with the phase component of any signal, or the differences in the shifts that might be there, the phase components of signals. And the easiest way to do that is make use of complex numbers. So our Fourier integral becomes, there's our signal, and we're going to multiply it by the cosine plus the sine of the same frequency. Okay? Now, of course, this is the continuous case, and if we've got this situation, we can express that as an exponential. Okay, so this is probably what we're more familiar with, is this the function multiplied by the exponential of with the complex exponential there. Okay, we can just expand this using Euler's formula. We can go both ways. Okay, you can see here that we have an inverse Fourier transform that allows us to take the frequency spectrum and to convert it back to the original signal. Okay, and we've got this scaling factor in this situation. But of course, in reality, performing a continuous integral is not really suitable. Okay, a number of reasons. One is the integral, as you can see if we went back, it's over minus infinity to plus infinity. And also, signals that we have are generally not continuous signals. They're sampled data or discrete data. Okay, so for this reason, when we're implementing Fourier analysis computationally, we use discrete Fourier transforms. Okay, where the integral is replaced by a summation, and so our expressions look something like this. So it's the sum of the sampled signal with n data points multiplied by this the different frequencies expressed in this exponential. Okay, so this is the discrete version of the continuous Fourier integral there. And similarly, we can go back and do the inverse. Okay, so we can flip between frequency and real space. You notice here we've sort of stopped using time and used k. So the question is then the sampling intervals. They're all related. So in real space, in time, or it can be distance, as in images usually. Okay. We're going to have a sampling distance between our two data points, in this case xn and xn plus 1. So the sampling rate, if we're dealing in time, is going to 1 over the difference between these data points, or 1 over delta t in time, or if we're using images in real space, position space, it's going to be distance to the minus 1. Frequency is the inverse of that, and we've also got this 2 pi scaling factor, where this is now in radians per second. For spatial frequencies, it's going to be sort of cycles or per unit distance, okay, or inverse unit distance. So our sampling period is number of data points that we have. So in an image, if it was 256 by 256 image, in one direction anyway, we'd have 250. N would be 256. We'll see this in a minute. And the frequency interval can be calculated using this, and the frequency range goes from minus twice the delta t up to 1 over twice the delta t. Okay. One of the features of this is that the frequency, when we transform to frequency space, the frequency spectrum, it repeats itself. Okay, so we only need to calculate it over the range, either minus 1 over 2 delta t up to positive 1 over 2 delta t, or we can go from 0 up to, these are the same. Okay, but so if we look at the frequency spectrum, it will just repeat itself every period of the signal. Okay, so MATLAB has fast Fourier transform functions for us, which simplifies everything for us. Now, I guess I think I made this point before. In a lot of, if you look at textbooks and theory and so on, they maybe start at 0. MATLAB, of course, starts at 1. Okay, so it doesn't make any difference really, but it just means that our summation starts at n equals 1 and goes up to n rather than 0 to n minus 1. The 0 frequency component is going to be contained in the first element of this transformed array. Okay, and the inverse discrete Fourier transform is given by this. So these are some examples of the application of that MATLAB fast Fourier transform. Again, these are just one-dimensional examples. I'll move on to two-dimensional examples in a minute. So this is actually a 50 hertz sine wave with 500 samples, so n equals 500. And I've also put some Gaussian noise on there. Okay, so there is a fundamental underlying 50 hertz sine wave there. We've got time along the x-axis. If we do the one-dimensional fast Fourier transform on that, what we get, here's our frequency spectrum. we've got these big two peaks, okay, and then we have some contribution at all other frequencies, which is due to this Gaussian noise. Okay, so you can see that what we're able to do by transforming this signal into frequency space, we're able to extract what the underlying frequency of the signal is there. Okay, and the magnitude of these peaks can give us information. The amplitude of these peaks can give us some information on, the contribution of that. So you can see that in this case, it's actually quite a good. We can see very clearly, and then we have some contribution of all the other frequency, the noise there as well. This is it's probably worth noting that this is actually because the Fourier transform is a complex entity. Okay, so it has a real and a complex part. We take the absolute part of it. So we just take the real part and plot that. Okay, if you try and plot the output of the fast Fourier transform, MATLAB won't like it because it obviously can't plot complex functions like that in this way anyway. So what I've also done here is I've just applied a smoothing algorithm. So one of the MATLAB smoothing algorithms to the data to remove some of the or reduce some of the noise. And again, you can see the effect on the frequency spectrum there. We've suppressed some of this higher frequency noise that's present in the signal. Okay, so you can see there very clear how the effect of smoothing on the frequency spectrum. The other things to note is that this repeats itself at from 0 to 250, 250 to 500. Okay, it's like a mirror image. That's something we need to be aware of. Yep.
Does that happen with noise? Is that like a common thing to happen, that it mirrors itself or not?
Yep. So it'll just repeat, and if we were to keep looking at frequencies at higher frequencies, we'd just see this repetition. Okay. Well, it's just because the data. If we go back, it is a repetition of. Where was it? The signal is just because it is a periodic signal that in frequency space, there'll be a maximum frequency, and because we're doing because we're sampling, we can't sample all frequencies, because if we had a larger data point, more data points, we would be able to see more frequencies, higher frequencies. So for, I guess, the integral, we would see a spectrum that extends out to infinity as well. But because of the nature of sampling, we're going to be able, that limits the number of frequencies we can actually access from the signal. Okay, so remember what we're doing is we're multiplying the signal by frequencies and adding up all the products of the different frequencies. Okay. So we can extend this to 2 dimensions. We're going to just repeat it over. So this is applicable for imaging. Okay. And again, there's an inverse to the fast Fourier transform as well. So this is the discrete Fourier transform. This fast Fourier transform is available in MATLAB. Probably should be a bit careful. I've called it, there is a function FFT, but when we're doing 2-dimensional fast Fourier transforms, we need to use FFT2. I probably should change that. Okay, there is a function for the images, which is FFT2. So this shows an example of a simple square type function in real space. So we had an image that was 0, and then we just had high intensity over a square region, and we do a Fourier transform of that. This is what the frequency spectrum sort of looks like. Okay, and this is actually you'll probably remember that if we have a square function that the Fourier transform of that is what we call a sinc function. Okay, and that's a two-dimensional sort of sinc function there. And if we display it as an image, it looks something like this. You'll also notice that what we've done is the zero frequency is in the middle, so we've had to do a shift. Okay, so there is also a MATLAB function called FFT shift that it sort of flips all the quadrants so that 0, 0 is in the middle. Okay, that's sort of more intuitive for us when we're the straight Fourier transform has the 0 in the four corners and then the highest frequency in the middle. Okay, but it actually makes more sense to us intuitively to have zeros at low frequencies in the middle and then extending out to high frequencies. So these are some examples. We've seen this image a few times now. Okay, so I've just displayed the original image. Then if we do a fast Fourier transform of it using this FF2 function, and we just display that, we just get this. It looks like there's nothing there. Okay, but what we actually find is there is actually some information in the corners. Okay, but we can't see it really because it's lost because we've got white there in the corners. So if we shift it using this FFT shift function, okay, 0 is now in the middle, and you can see we get this big high peak. Okay, and again, it doesn't look particularly interesting. Okay, and the reason for that is because we've got this big, a lot of information at quite low frequencies, and that's dominating our image when we scale it, when we display it. Okay, so what we can do is use a log scale to plot the magnitudes or intensities in our Fourier transform, and then we can start to see some information there. Okay, so this is the log of the Fourier transform. This is something we only do for display purposes. Okay, just to allow us to be able to see the frequency information because it's dominated. Most frequency spectra are dominated by low frequencies, so we get a big spike in the middle there, and that's going to, when we display it, it sort of dominates the display there. Okay. This is another CT image which shows a similar thing. So when we do the direct 2D Fourier transform, it looks very uninteresting. If we shift it, there's our big spike at low frequency, 0, around 0 frequency, but then if we rescale it, we get this. We can start to see some of the frequency information there. Okay, so what you generally find is as we go further out, this is to higher frequencies, that's where the sort of noise is. Okay, but also it's worth noting, this is the detail in the image as well is contained in the higher spatial frequencies. So, filtering in the frequency domain. Okay, what we're going to do is effectively perform this operation, and then we're going to modify the frequency spectrum, the two-dimensional frequency spectrum. We're either going to, a low-pass filter we're going to remove, we're going to keep the low frequencies and remove high frequencies, and then a high-pass filter is the opposite. Okay, and then a Butterworth is sort of rather than having an abrupt cut-off frequency, we have a smoother transition. So the basic method is we compute the Fourier transform of the image. It's a 2D Fourier transform. And then we use some sort of filter transfer function. And then we do an inverse transform back into real space, and that's our filtered image. Okay, so the two Fourier transform functions are FFT2 and IFFT2. Okay, so the intention here is we're going to modify the frequency spectrum in some way. Okay, and this could be either enhancing desirable frequencies, which is the signal, but more generally we're going to maybe remove unwanted frequencies, and this is generally some sort of noise component in the signal. So the ideal low-pass filter looks something like this. Okay, so we're going to essentially allow frequencies below a particular frequency, and remove anything that's got a frequency higher than some cutoff. Okay, and this is how we express that mathematically. So we've got a two-dimensional frequency space, the two U and V here. So if it's less than the D naught is the cutoff, we're going to have the signal equal to 1. If it's greater than that, so at higher frequencies, it's going to be 0. Okay, so if we take a sort of 1D look at that, it looks something like this. Okay. So this is how we can implement this in MATLAB. So we're going to, normally what we do is our cutoff is going to be some fraction of the maximum frequency. Okay, so we'll have a maximum frequency, and then we're going to, in this case, I've set it to 0.2, so that's where our D naught is going to be, is 0.2 of the maximum frequency in the frequency image. Okay. So that this the image quite often, if it's not square, we will define the radius of the filter to be along the shorter image dimension. So the shorter image dimension is going to be the minimum of x size and y size, which are the sizes of the image. Okay, and then we're going to work out what the radius is. So this is our D naught. I probably should have called it D naught, so it's just not confusing. But it's if we go back, so it's the radius of this, or this distance here. Okay, we work that out just using trigonometry. So it's 0.2 times that. So what have we got here? The minimum of this is the actual radius. Okay, and then we square it. It's given by this expression here. And then we multiply by 0.2. And then we can do it. The easiest way to do it is just with a loop. So we loop over every pixel and just do a check to see if the pixel's inside or outside the cutoff frequency. And if it's, in this case, outside that cutoff, we're going to set it to 0. Okay. Remember, this is the Fourier transformed image here. So there's obviously a load of, I've transformed the image further up. So this is an example of that low-pass filtering on this image. So there I've done the Fourier transform. We've rescaled it just for display purposes. And then this shows the filter applied to that. So there's the circular region. We're going to eliminate frequencies greater than this 0.2 of the maximum, okay, and only allow the frequencies less than that. And then this is the filtered image. Okay. So low pass, remember, is going to be eliminating higher frequencies. So we're losing some of the resolution there, or some of the sharpness in the image, okay, as well as eliminating any random noise which might be in there. We're also going to be losing sharpness in the image. So the ideal high pass filter is the opposite. So it's in 2 dimensions. You can imagine it's like this sort of 0 in the center, and then we have a value of 1 outside that circular region. So it looks something like this in 1 dimension. So we can apply it. There's the Fourier transform, the compressed version of it. There's our filter applied to it. Okay, so you can see we've set all frequencies, all the low frequencies below this certain cutoff. We removed those, and then this is the filtered image. So here we're enhancing. We're sort of, I guess we're. So we've done an inverse. I should probably make it clear. We've done an inverse Fourier transform of this filtered spectrum. Okay, and you can see what we're left with is the sharp detail, high frequency information that's in the image. Okay. And that's how I've implemented it. It's exactly the same, except we've flipped that sign around. Okay. There is a problem with this, though. When we have an image with very sharp edges. So if we have an original image, the extreme case is where we just have a rectangular object and we apply our filter, we get an effect known as ringing. So we get these this sort of effect in the filtered images. So this is the high pass filter and the low pass filter. Okay, it's an artifact from this performing this filtering in frequency space. So one way around this is to use this Butterworth filter. So this, rather than having that abrupt cutoff, it has a smoother transition so we don't just have 0 or 1 at the cutoff frequency. We have a smoother, and I'll show a diagram of it on the next page. Okay. So there's the ideal high-pass filter, and this shows the Butterworth high-pass filter. Okay, so that we've got a smoother transition when we're modifying the frequency spectrum. So it looks something like this. Okay, and that eliminates that, or to a certain extent, the ringing effect. So this is the low-pass filter. So instead of remember the sharp cutoff, we get this is in 2 dimensions. We get this shaped function. Looks something like this in frequency space, and if we take a profile through it, it looks like this. And these are the different orders. Okay, so if we went back to the expression, we can change the order of the filter n here. Okay, and that's going to affect the slope. We can also change the d0. That's like our cutoff frequency for the high pass, the ideal filter. Okay, so we can shift this in frequency by changing d0, and we can change the order of it which affects the sort of the transition. So that's 2 parameters we have at our disposal there. These are just examples again. This is just showing the ideal high pass filter and then the Butterworth high pass filter. Okay, that looks something like that. So this is if we just do the ideal high pass filter, we get the ringing effects, and if we do the Butterworth, we lose those. The other thing we can do is we can emphasize the higher frequencies, and we can do that just by introducing this constant C to the filter. So again, remember that expression for our filter. So this, we would just multiply it by some constant. Okay, and then you can have a go at this in the assignment. We're going to apply a Butterworth filter and then try different values and boost, see the effect on the boosting of the higher frequency. So this is an image of Saturn, and you can see that when we do the high emphasis, we get a sort of we can see more detail in those in the gas clouds and the rings as well. Okay, so assignment 3 is going to be to demonstrate image enhancement in the frequency domain using Butterworth filters. Okay, so we're going to apply a second order high pass Butterworth filter to the image Saturn.bitmap, which we saw on the last slide. Okay, that should be available on Blackboard as well to download. And try what I want you to do is try a range of the cutoff values. Okay, and comment on their effect on the filtered images, and then go on to do a high boost second order high pass Butterworth filter by using trying a different range of C values, and commenting on the effect of these on the filtered image. Okay, so again, you're going to be sort of writing some script to solve these 2 questions or answer these 2 questions, applying these filters, and then you're going to just give some explanation of what you did and the results you got. Okay, and then submit the script as well. Okay. Any questions on that? So effectively, what you've got to do is, I showed you the ideal filter. Let's go to it's the ideal high-pass filter. You've just got to modify this, so rather than it being 1 or 0, it's going to be this smooth. You're going to have to look through each pixel and calculate the transfer function according to that expression, okay, which was this one, or the high-pass filter is this one, okay. Well, you're going to, well, no, because we've just sort of said if it's inside, or we just sort of said if it's inside the circle, we set it to 1 if it's 0. What you're going to do for each pixel, calculate this function, HUV, where we've got, you can calculate that using, that's the circular bit, yeah. So this is the R2, I guess. It's not a constant in this case. It's it's going to be different for each pixel. Okay. So start off maybe with, do it in terms of D0 will be 0.2 of the maximum frequency, I suppose. Okay. So have a think about it first. Just plan how you're going to, the usual thing, you're going to read in the image. Familiarize yourself with the MATLAB functions, fast Fourier transform 2, fast Fourier transform shift. So maybe just go through that process of Fourier, maybe implement a high pass or low pass filter first, and then think about how you're going to modify it for the Butterworth filter.